let's look at the fifth problem on the first homework. So given a set of points, one of these points is Pareto optimal if there are no other points in this set that are to its top right. So the naive algorithm for doing this is just to go over every single point and check it against every other point, which would be n squared, because it's n points, and for each point you're checking n minus 1 other points. But we want to do better. We want to get a O of n log n time algorithm with divide and conquer. Now, there are many ways to divide this problem into smaller problems, and it will take some testing to figure out which ones will actually get you to the desired runtime. But one intuitive way is to split it into, say, a left subset, to split P into a left subset and a right subset, or to split it into, say, top and bottom subsets. Either of these will work. It will just result in an algorithm that basically swaps how it treats x and y. But let's go with the left and right split. So we'll divide the points evenly into left and right subsets. And you can do this by sorting them by x value and just taking the half with the smaller x values to be in the first set and the half with the higher x values to be in the second set. Let's call these L and R. So clearly P is the union of L and R. And since we're running a divide and conquer algorithm, we'll be recursing on each of these subsets. So suppose L prime is the result of running this function on L, and R prime is the result of finding the optimal points in R. Clearly, L prime is a subset of L, and R prime is a subset of R. Now we know the set of optimal points in each of these subsets, and wish to use this information and maybe some extra computation to figure out which points are optimal in P overall. The easier part is to figure out what happens to the optimal points from R prime. So clearly these 2 points would be in R prime, but and this point would also be in R prime, but this point will not be in R prime because there is a point in R that is to the top right of it. So any point that is in R prime, we can see that it'll also be in P prime, as in it's also Pareto optimal in P. The reason for this being that any points, it was optimal in R, meaning there are no points in R that are to its top right. So the only new points you introduced when you move back to P are the points in L. But since these are to the left of it, there's no way they're to the top right of it. So any point that is optimal in R is also in P prime. And so we know R prime is also a subset of P prime. The more involved part of this problem is to handle what happens to point in L. Say this point will be classified as a optimal point, as a Pareto optimal point in L, because there are no points in L that are to its top right. However, there is a point in R that is to its top right. So clearly, not every point in L prime is in P prime. But how do we distinguish which ones should be in P prime? Well, let's consider why this point. Let's first consider the fact that for any point in L that's Pareto optimal, you can always guarantee that there's a point to the right of it simply because there is a right subset. And so in order for it to be Pareto optimal, you must guarantee that there are no points that are both above and to the right of it. And the fact that it is in L prime tells you that there are no points in L that are to the right and on top of it. And so your concern is with points in R that are on top of it. Because they're in R, you already know they're to the right of it. So your only concern is whether these points are on top of it. And so we can argue this if and only if relationship that a point in L prime is in P prime if and only if there are no points in R that have a higher y value than this point in L prime. This goes in both directions. For example, you see that since there are no points with higher y values in R than this point in L prime, there simply cannot be any points to the top right of it, because any points that are because we know that there are none of these points in L, and in R, since none are on top of it, there are also none that prevent it from being optimal. And in the other direction, let's suppose that this point is in the optimal, but somehow not in let's suppose this point is in L prime, but somehow not in P prime. Then it must have been the case that some point in R prevented it from being optimal. So some point in R was both to the right and on top of it. And so we can write the condition. We can write the set P prime as some combination of L prime and R prime. So first we know all of R prime is in it, and then we'll take the union of that with some subset of L prime that satisfy our previously discussed criteria. So this will be a subset of all of these points will have to come from L prime. Now the criteria is that the y value of this point in L prime is greater than the y values of all points in R. And let's just call that value y max. The criteria is the y I is greater than or equal to y max. And the y max is max of xj, yj of the points in R of yj. So that tells us the logic of how to produce p prime, but we still have to figure out the algorithm in its runtime. In pseudocode, you can imagine an algorithm like this. Let's just call the function f of p. It acts on p. And so the first step is to split p into L and R, and then recurse to get L prime and R prime. Now you will create a new set p prime, set it to R prime first, and then we'll add in all the points in L prime that satisfy our requirements. But before you do that, you first have to figure out what this y max is, and you can do that with a linear scan for the greatest yj value. And then you add in points from L prime into p prime. So for xi, yi in L prime, if yi is greater than y max, add it to p prime. And then in the end, you just return p prime, and you're done. So finally, let's look at the runtime of this algorithm. So in each call, you're making 2 recursive calls, each on inputs of size n over 2. And now let's look at the constant. Now let's look at the extra work that goes into this function call. So you're doing one linear scan here and another linear scan here. So there's at least O of n. Now you might be worried about, well, how do we split the points into 2 halves? Well, you can do this. You can do some pre-processing that makes this constant time, actually linear time. And what you do is, before you run any of these recursive calls, you sort all the x values from left to right. So pre-processing, sort p by x value. And then whenever you make these partitions, you can just take the first and second half of these sorted values, the sorted points. And that would be O, the sorting would be O n log n added to the overall runtime. But let's first consider this runtime from the recurrent relation. So if you apply the master theorem, you'll get that T of n is O of n log n, and our sort is also n log n. So this is just the overall runtime. And that's the runtime of the algorithm.